if you pick any point on the space-time diagram, like this black point here, in one coordinate system, we will have some x-coordinate, spatial coordinate, and some time coordinate. But in another frame, if you're using these axes, you will need to drop lines towards the axes which are parallel to the axes. So if you want to figure out what spatial coordinate this point has in the x prime ct prime coordinate system, you need to follow a line that is parallel to the time axis, and all these points are at the same place, same spatial place in the x prime ct prime coordinate, and you can sort of look at where it hits the x prime coordinate and read off the spatial position in the x prime coordinate system. And to find the time, you need to follow the line which is parallel to the space axis, which connects points that are at the same time. And you look at where the line intersects the time axis, and you will be reading off your time coordinate from the number that you can read off from the axis. Everybody okay with this? Okay, when I teach relativity, many students have problems with these tilted axis situation, but once you get used to it, it's not that difficult. And the most important thing about the Lorentz transformation is that the spatial axis gets tilted when you go from one frame to another. So 2 points that are at the same time in one frame are no longer at the same time in the other frame. Okay, so let's see, if I look at this point, and this point, which lie on the horizontal line in the xct coordinate system, they have the same t coordinate, so they are at the same time in frame A. But if you go to the diagram on the right, the 4 points, the 5 points that we just looked at are no longer lying on a line parallel to the x-axis, so they are not at the same time anymore. And this fact is the most important point about relativity, and it is one of the hardest things that students have in understanding relativity, because the idea that if two things happen at the same time for one person, it has to happen at the same time for everybody else, is very deeply ingrained in our intuition. So that is one of the things that's very difficult for students to accept.
Quick question.
Yes.
So this second diagram, which is kind of representing the Lorentz transformation, like, so it is including both boost as well as rotation, right?
Oh, this is only a boost diagram. I am ignoring rotations right now because I only have one spatial axis. So I'm boosting in the x direction, and
Okay.
I'm ignoring y and z.
Okay, thank you.
Okay, and since we just talked about rotation, I would like to point out that the Lorentz transformation is actually very similar to rotations. Okay, like on the left, I show two coordinate systems x, y, and x prime, y prime, which are rotated relative to each other. And on a two-dimensional plane, you can associate two coordinates x and y to any point on the two-dimensional plane, but naturally, the two numbers you'll be using will be different depending on which coordinate system you're using. And in the case of rotations, x squared plus y squared is equal to x prime squared y prime squared, because the distance from the origin is going to be invariant. And Lorentz transformation, the situation is analogous, except instead of time squared plus space squared, it's time squared minus space squared that is conserved when you go from one frame to another. So it's ct squared minus x squared that is equal to ct prime squared minus x prime squared. Okay, and the Lorentz transformation equation that I showed you earlier can basically be derived by this requirement that this object stays invariant when you go from one frame to another. And I hope that's okay. Okay, so as I just said, if we understand that Lorentz transformation diagram, we can derive everything we need to know about relativity from that diagram. And one of the first things that we can tell is that because the lines that connect points that are at the same time is different depending on which frame you're using to describe your space-time. On the left, on the diagram on the left here, I have a diagram of 3 clocks. So, and they are ticking away from bottom to top as time progresses. And I am showing on the left the 3 clocks that are synchronized in the frame that is at rest. Okay, so this is the situation where I have 3 clocks ticking away in frame A, and this clock, and this clock are at the same time in frame A, and they are giving the same reading. These 3 clocks are giving the same reading in frame A at the same time, and so on and so forth. So an observer in frame A, at rest in frame A, will say, oh, all these 3 clocks are synchronized because they are giving the same reading at the same time. Okay, on the other hand, if you are looking at the same 3 clocks from a frame which is moving to the right, and I have a drawing of a car here to represent that frame. If you are observing the same situation from a different frame where this is the time axis and this is the space axis, then from the moving frame's point of view, this point is at the same time as this point, which is at the same time as this point, and this observer will look at the readings of the clock and say, well, these 3 clocks are giving different readings at the same time. So this observer will argue that these 3 clocks are not synchronized. Okay. And on the right, I show a situation where I have 3 clocks, but these 3 clocks are now moving together with the car frame. They're moving to the right at the same speed as the car. And as you can see, this clock, and this clock are all giving the same reading. And so are this clock and this clock and this clock. So as these clocks ticks away in frame B, the observer in frame B will argue that these clocks are synchronized because they are giving the same reading when they are at the same time. Whereas the observer in the other frame, which is at rest, will look at this reading of the clock, this reading of the clock, this reading of the clock, and because they are all different, this observer will argue that these clocks are not synchronized. Okay, so it's important to understand that in the case when you're looking at time from different frames, it's not just that the reading of the clocks may be different depending on the frame that you're using. Clocks that may be synchronized in one frame may not be synchronized in another frame. So when we talk about the reading of a clock in the respective frames, we have to specify which clock we're talking about. Okay, I hope that's clear. Okay, so if the so basically what Lorentz transformations are telling us is that the concept of simultaneity, namely the concept of 2 events happening at the same time or not, is going to depend on the frame that you're doing the observation from. So in this picture, in this figure, I show 2 points which I label A and B. And in the frame given by the axes x and ct, I think it's clear that the time coordinate of A is smaller than the time coordinate of B. So in the XCT frame, A is happening before B. Hope that's clear. Okay, now if we look at the same points from a frame moving to the right, and I'm showing the x prime ct prime axes are actually showing a frame which is moving at half the speed of light to the right, then it turns out that point A and point B are actually on a line that connects points that are at the same time in that frame. So in this moving frame, the x prime ct prime frame, A and B happen to share the same time coordinate, so they are happening at the same time. Okay, now if we go to another frame which is moving even faster to the right, given by the x double prime and ct double prime coordinate axes, in this situation, to find the time coordinate of A, we need to draw a line parallel to the space axis, which is x double prime axis, and look at where it crosses the time axis. So the time coordinate of point A is up here. You can read it off from here, whereas the time coordinate of point B will be down here. So this is a situation where in the frame xt, A happens before B. In frame x prime t prime, A and B are happening at the exact same time. And in the frame x double prime, ct double prime, B is happening before A. Okay, so you can have two events happening somewhere in space-time, but the chronological order could be different depending on who is doing the observation. You know, which inertia frame you're doing the observation from. Is everybody okay with this? This is kind of, difficult to understand for many beginning students, but I think this should be emphasized, because if you fail to grasp this, then all of relativity will become very, very mysterious. Okay, so if you have two events whose chronological order can depend on which frame is being used to do the observation, a natural question that would come up with, won't that contradict causality? Okay, for instance, we can take the same diagram and imagine sending something from point A to point B. For instance, we can imagine firing an arrow at point A, and the arrow, we will make the arrow follow this line that connects A and B. And at B, we can argue that, we can set it up so that the arrow will hit an apple or something like that. Okay, let's imagine that we could do that. Then in the frame fixed to the ground, the arrow will be fired first, and then the apple will be hit later because B happens after A. But in the moving frame, in the frame which is moving at half the speed of light to the right, A and B happen at the same time. So the speed of the arrow will be infinite because it takes 0 time to get from point A to point B. But if you look at the same situation from a frame which is moving even faster to the right, then B happens before A, and you encounter the peculiar situation that the apple is hit by the arrow before it is fired. Okay, and that doesn't make any sense whatsoever. And I think bright students who pay attention to what you're talking about will immediately ask you a question saying, won't this be a problem? And the answer, of course, is that yes, it is a problem. Okay, but the reason why it became a problem was because this the arrow that went from A to B travel at the speed faster than the speed of light. Okay, in this space-time diagram, we use x and c times t as the coordinates. Then the light beam that's ejected from A, a light pulse that's emanating from A will follow this red line, which makes a 45-degree angle from both the horizontal and vertical axis. And you can tell that this line that connects A to B has an angle which is larger than 45 degrees from the vertical, which means that it's going at a speed much, much faster than the speed of light. Okay. And whenever you allow anything to travel faster than the speed of light, then you encounter this contradiction, because if you take any 2 points along that line, the chronological order of the 2 points is going to depend on the frame from which the observation is being done. Okay, so we hear stories like relativity claiming that the speed of light cannot be exceeded. And if you watch science fiction movies or science fiction TV programs, we often hear about imaginary technologies like the warp drive or whatever that will allow you to exceed the speed of light. But the reason why relativity does not allow you to exceed the speed of light is because if you could exceed the speed of light, causality will be broken. You can have a situation where the effect happens before the cause, which is kind of peculiar. It's like, you're born before your grandparents are married, kind of situation. So, the students should be made to understand that the upper limit that we have on the speed of travel or light propagation, or even if it's a signal, you cannot have a message being received before it's sent. So nothing can exceed the speed of light, and it's because of causality, not because it's a technological hurdle or anything like that. So it is difficult to imagine that something like a warp drive will allow you to travel faster than the speed of light. And I'm pretty sure this will be very disappointing to many sci-fi fans that you may have in your classroom, but c'est la vie. Okay, so so in a space-time diagram, if you pick any point on the space-time diagram, you can draw these lines that are at a 45-degree angle from both horizontal and vertical. And these red lines emanating from point A are the light pulses, the paths of the light pulses that come out from A. And all the points in this upper triangle here can be reached by a line along which the speed will be smaller than the speed of light. Okay, so all these points are the points that can be affected by whatever happens at A. So the points in this triangle are the points that are in the future of A. And in a similar fashion, all the points in this lower triangle are the points such that if you send a light signal from any point in this triangle, if you send a signal either at the speed of light or any speed smaller than the speed of light, then that signal or whatever you're sending can reach point A. So all these points can affect A, which means that they are in the past of A. Okay. On the other hand, all the points in this right triangle or all the points in this left triangle, the chronological order of any point in this left and right region can change the chronological order of the point with respect to A can change depending on the frame that you're doing the observation from. So you can pick any point in this triangular area, and that point could be happening before A, or at the same time as A, or in the future of A. So so any point cannot be affected by any point in this region or this region cannot be affected by A or cannot affect A unless you sort of use a signal which is traveling faster than the speed of light, which you don't want to happen. So these are the regions which have no causal relationship with this point A. Okay, I hope everybody's okay. And this diagram is known as a light cone diagram. And it describes which points in your space-time are in the future, in your future, and which points are you in your past, and which points cannot have any causal connection to your point. Okay, and this may not look like a cone, but if you have multiple spatial dimensions, like if you have two spatial dimensions, the diagram looks like a cone, and the inside of the future cone is what you call your future, and inside your past cone is what you call your past, and outside of your cone are neither. And you cannot have any causal connection with any of the points outside of your light cone. Okay, so I hope this is clear, and if we explain this sufficiently to the students, I think they will stop bugging you about warp drive and things like that. Okay, so now that we have the basic idea of how Lorentz transformations work, I would like to explain what time dilation is. Okay, and when we are talking about time dilation, we're basically comparing the reading of two clocks to see if they are running at the same rate or not. Okay, and you may think that I'm sort of pointing out a very trivial point, but if you are comparing the reading of two clocks, you have to compare the readings of the two clocks at the same time, right? Like if I have, if I want to compare whether my watch is running properly or something against the, what my smartphone is telling me, then what I would do is I would put my smartphone and my watch side by side and read the readings at the same time, and first check that they're giving the same reading initially, and then I would wait an hour or something, and then compare the readings of my smartphone and the watch and try to see if they still give the same reading. And naturally, we read the two clocks we're comparing at the same time in the beginning, and we compare the readings of the clock at the same time at the end. Is everybody okay with this? Because it doesn't make sense for me to compare my smartphone and my watch at 10 o'clock in the morning, and then I wait until the afternoon, and I read one clock at 2 p.m., and I read the other clock at 4 p.m., and if I say, wait a minute, the clocks are not giving the same reading, you would say, that's ridiculous. You have to sort of read off the two clocks at the same time, right? I hope everybody's okay. Okay, now if we're comparing the readings of two clocks that are at rest with respect to each other, we can just let them sit right next to each other and compare their readings at the same time at any time we like. Okay, but if we are trying to compare the reading of two clocks that are not in the same frame of reference, then we have a problem. Okay, because we first need to make sure that they're giving the same reading in the beginning, and then we need to compare the readings sometime later to see if the readings are still the same or not. Everybody okay with that? Okay, now because we need, the observer who is at rest on the ground and the observer who is moving with the clock they need to agree that the two clocks are giving the same reading at the same time. The only way you can do that is when the two clocks are at the same place, right? Because if I can backtrack a little bit to this diagram I had here, there's not much meaning in comparing the reading of this clock, for instance. Let's see, the reading of this clock, which is at rest, and this clock, which is moving, because Because if the clocks are at different spatial positions, then naturally, the observer on the ground will say, well, this clock is at the same time as this clock, which is at the same time as this clock. But the observer who is moving will say, no, 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 this clock is at the same time as this clock. Okay, so the observer on the ground may want to sort of compare this reading with that reading, but the moving observer will want to compare this reading with that reading, which doesn't make any sense. And the only time that both observers will agree that the moving clock and the clock that is at rest are giving the same reading at the same time is when they're at the exact same spatial position. So when you're comparing two clocks when one is moving relative to the other, you have to sort of make sure they give the same reading when they pass by each other, when they are at the same spatial point. Okay, I hope that's clear. So we have two clocks. One is moving to the right together with the right moving observer, and one is staying put at the origin. And we assume that the two clocks are at the same spatial position initially. But as time goes by, the two clocks will necessarily move away from each other. And as they move away from each other, when the two observers compare the readings of the clocks, they have to be compared at the same time, but what at the same time is for each observer will be different. For instance, when the grind frame observer is looking at the reading of clock at B or something, naturally the reading of this clock will be compared with the reading of the other clock at this space-time point, because point B and point D are at the same time in the rest frame, in the ground frame. Okay. However, in the moving frame, this clock and this clock are not at the same time. B and C are not at the same time. It's actually B and E that are at the same time. Okay, so naturally, from a moving frame, the readings of the clocks that should be compared is the reading at point E and point B. Okay, but from the rest frame's point of view, the reading of B should be compared with the reading at D. Okay, so when the rest frame observer compares the reading of the other clock with the reading of the clock that is not moving, the rest frame observer will compare this reading and this reading, and he or she will conclude that the moving clock is running more slowly. Okay, but the moving frame observer will say, well, that's ridiculous, because the rest frame observer is comparing the reading of the clock at rest with the reading of the clock in the moving frame in the past. Okay, but however, when the moving frame observer compares the reading of his clock here and the reading of the other clock here, the rest frame observer will say, well, that's ridiculous, because this clock is at the same time as this clock. So the reading that should be compared is the reading of the other clock at E with the reading of the rest frame clock at C. Okay, because B happens in the past of C. So each observer is going to think that the other observer is doing something ridiculous, because the other observer is always comparing the reading of the other observer's clock with the reading of your clock in the past. Okay, and if I draw a diagram in which both observers are treated in the same fashion, you can imagine, if I draw a diagram in a frame in which both observers are moving but in opposite directions at the same speed, then the diagram will look like this. And the reading and point B will be here and point D will be down here, and B and D are at the same time for the left moving observer. Okay, but point D but for the right moving observer, point B is at the same time as point E. But for the left-moving observer, point E is at the same time as C. So when the two observers compare the readings of their clocks, they will always be comparing the reading of the clock that's moving with them with the reading of the other clock in, at the same time in their frame. But from the other frame, it will always look like the reading of the clock is being compared to what it was in the past. Okay, and this is where time dilation comes from. And because you're always comparing the reading of your clock now with the reading of the other clock in what the other observers thinks is the past, you end up finding that the moving clock looks like it's always running slow compared to your clock. Any questions here? I hope everybody's okay with this, okay? Many students are confused when you tell them about time dilation because they think, how can the relation be symmetric? And the relation can be symmetric because one observer will be comparing the reading of this clock with that clock, but the other observer will be comparing the reading of this clock with that clock. So they are comparing two totally different things. Okay, so when you compare the reading of this clock with this clock, the reading of this clock will be advanced compared to reading of this clock, and this observer will conclude that, oh, the other clock is running slow. But the moving observer will compare this reading with that reading, and the moving observer will conclude that, oh, the other clock is running slow. So each observer will think that the other clock is running slow, but there's nothing wrong about this because because their concept of at the same time is different, and they'll be comparing the readings of clock at different times, so to speak. Okay.
Actually, can I quick add something to this? Like, probably this will be the best idea to also explain the twins paradox, right? Like, so because that they are also in the different frame, and so one is saying that other clock is slow, right?
Yes, I'm getting to that.
Okay, thank you.
Okay, so and this leads to the twin paradox. Okay, so imagine that you have twin siblings or something, and one sister stays on the Earth, and let's assume that the other sister takes a trip to outer space on a rocket ship, which is moving very, very fast. And in the Earth frame of reference, because the rocket ship is moving at very high speeds, the Earth frame observer will think that time in the spaceship is passing at a slower rate. So when the spaceship comes back, the Earth frame observer will expect the other sibling to be younger than she is, right? Because time on the spaceship is passing more slowly. But from the spaceship point of view, it's the Earth that's moving. And because of the symmetry of time dilation, this spaceship observer will observe time on Earth to be passing at a slower rate. So at the end of the trip, naturally, the spaceship observer will predict that the sibling on the Earth will be the younger of the two. And the question is, how can both points of view be correct? You cannot have twins where one is older than the other, and and vice versa or something, and both points of view cannot be true at the same time, right? So what is the resolution to this mystery? And this space-time diagram explains it. And the important thing to understand is that the two siblings, the twins, are not actually treated in a symmetric manner, because for the spaceship to come back to the Earth at the end of the trip, it has to turn around somewhere. Okay, so if the spaceship is moving to the right along this line in its outbound trip, and if it turns around and heads back in the opposite direction at point C, then the frame of reference that the spaceship is in is different. The spaceship will be in one frame during the first half of the trip, but in the latter half of the trip, the spaceship will be in a different frame of reference. Okay, and when you look at a point C in the outgoing frame, in the right moving frame of reference, point C is at the same time as point A. Okay, because A and C are connected by a line which is parallel to the spatial axis. Okay, on the other hand, after the spaceship has turned around, point C is actually at the same time as point B. Okay, because in the left moving frame of reference, the spatial axis is tilted downwards. Okay, so what happens is as the spaceship starts out from the origin and heads off to C, throughout the trip, the spaceship will see the clock on the Earth ticking at a slower rate. Because when the spaceship gets to C, the clock on the Earth is still at A. And the spaceship observer will say, oh, less time has passed on the Earth than the time that has passed on the spaceship. Okay? Now, after the spaceship has turned around, point C will be at the same time as point B. And when the spaceship observer, keeps track of what's going on the Earth, the spaceship observer will see the Earth clock progress from B to the final point where they meet. And just like in the outbound trip, less time will pass on the Earth in the return trip. However, when the spaceship turns around, time on the Earth suddenly jumps from point A to point B. Okay, because before the turnaround, point C was at the same time as A, but after the turnaround, point C is at the same time as B in the moving frame. So because of this huge jump, when you add all the effects together, it turns out that time on the Earth will have more time will have passed on the Earth than the time on the spaceship. Okay, the Earth frame observer will see time on the spaceship passing at a slower rate than on the Earth, and the Earth frame observer will see that happening both during the outbound trip and during the return trip. And the same thing happens for the spaceship observer, except at the turnaround, the point that is simultaneous on the Earth will jump from A to B. So from the spaceship observer, it will look like time on the Earth has suddenly jumped into the future. Does this make sense?
How do I explain to a student asking the question, and of course, that is a question from me also, so that turning around is not a constant speed situation. Like, so turning around takes place, when turning around takes place, the physics there is different, right? How do I reconcile that?
It's I don't think you need to sort of talk about the details of how the acceleration happens. It's just that if you accelerate, you're basically jumping coordinate systems. You're going from one inertial frame to another, and every time you switch, and in this diagram, I drew it so that the change in direction happens instantaneously, but you can imagine it's happening more gradually, but it doesn't change anything because as the spaceship turns around and changes its direction, the line that is connecting the points that are at the same time will change its tilt. It will start out with tilting upwards to the right, but as the ship moves around, it will sort of start turning over eventually, and when the ship starts to move towards the left, it will be sort of slanting downwards to the right. And so instead of jumping from A to B instantaneously, if the acceleration is gradual, time will sort of pass very quickly from point A to point B.
Thank you.
So that is time dilation, and it happens because the concept of what points are at the same time will depend on the observer. Now, when you're thinking about measuring the lengths of objects, say the length of a moving train car, again, you may think this is something that is obvious, but what you mean by the length of something is the separation of the ends of the objects at the same time, right? And if the object is not moving, since both ends are kind of fixed, then you can just measure its natural length at any time you like. And you don't necessarily have to sort of measure the position of the right and the left end at the same time if they're not moving. But if you're looking at an object which is moving relative to you, then naturally you want to figure out where the right end of the object is and where the left end of the object is at the same time. Agreed? Like if you have a moving object, you're not going to measure the position of the nose at 11 a.m. and measure the position of the tail at 11:05 or something like that, and say that the difference is going to give you the length of the object. Naturally, you need to figure out where the right and the left end are at the same time and measure the difference between the two, and that is going to be what you would call the length. Okay, so imagine that you have a train car speeding to the right, and on this space-time diagram, this red line is the whirl line of the tail of your train car, and this red line is the whirl line of the nose of your train car. And if you're an observer on the ground, and if you want to measure the length of the train, you will naturally pick 2 points that are at the same time, like point C and point D, and measure the spatial locations of point C and D, and say that the spatial separation of C and D is the length of the train. Okay, or you could pick another time, like point A and point B, which are at the same time in the ground frame, and say the separation of point A and point B is the length of the train. Okay, however, A and B may be at the same time in the ground frame, and C and D may be at the same time in the ground frame, but they are not at the same time in the moving frame of reference. So if you're sort of looking at the same diagram from the train frame of reference, the frame fixed to the train, it will be C and B, which will be at the same time. So naturally, from an observer's riding the train, the spatial separation between C and D is what the moving observer will consider to be the length of the train. Okay, whereas the observer on the ground will say, no, 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 no. The separation of C and D is not the length of the train. It's the separation of A and B, or the separation of C and D. What the other observer is claiming to the length is ridiculous because C and B are not at the same time, right? And but because of this, the length of objects will naturally be observed to be different depending on who is doing the observation, and moving objects will always look like they are shorter than when they are at rest. And to see the effect most clearly, I think it's best to treat the two observers symmetrically. So imagine that you have two train cars that are moving in opposite directions with the same speed, but in opposite directions. Then this black line and this black line represent the nose and tail of the train moving to the left. And this red line and this gray line represent the nose and the tail of the train moving to the right, say. Then the right moving frame of reference will be given by the x prime ct prime axes, and the left moving frame of reference will be given by the x and ct frame of reference. Okay, and in the right moving frame, naturally, the observer riding the right moving train will compare the locations of the tail of his or her train, the nose of that train you're riding, and the nose and the positions of the nose and tail of the other train car. So at point A, the nose of the left moving train and the tail of the right moving train are at the same position. And the points that are at the same time in the right moving frame are points B and C. Okay, so in the right moving frame, the length of the right moving train is the spatial separation between point A and point C, whereas the length of the other train is the spatial separation between point A and point B. And AB is obviously shorter than AC, so the moving train will look like it's shorter compared to your train. But if you're an observer riding the left moving train, point A is at the same time as point E and F. And the separation of A and F is the length of your train, and the separation of AE is the length of the other train. So the other train looks shorter compared to your train. Okay, so this shows that when you're thinking about Lorentz contraction, it's always the moving thing, whatever that's moving relative to you, that looks shorter compared to what is at rest in your frame of reference. And again, there is no contradiction because you are comparing different points. In the right framing, right moving frame, you are looking at the spatial separations of points A, B, and C. In the left moving frame, you're looking at the spatial separation of points E, A, E, and F. So you're looking at completely different sets of points. So there's no contradiction in saying that in the right moving frame, the left moving car looks shorter than the left looks shorter, but in the left moving car's frame, it's the other way around. Okay, and it's all due to the fact that you have to compare the separation of points at the same time, but what you mean by at the same time is going to be different. And I think using these diagrams to explain this is much easier than trying to manipulate equations, because if you try to derive the same result using equations, even you can get pretty confused quite easily. Okay, let's see. So let me show you another paradox that involves the Lorentz contraction. Imagine that you have a tunnel at rest on the ground, and there's a train that's moving to the right and zooming through the tunnel. Okay, so this vertical line is the entrance of the tunnel, and this vertical line is the exit of the tunnel, and this line that's moving to the right is the tail end of the train, and the other line which is parallel to that is the nose of the train. And the train and tunnel are assumed to be at the same length when the train is at rest. Okay, now imagine that there is a door on both the entrance and the exit of the tunnel, and when the door on the exit will open just to let the train through, and the door at the end in the entrance will open just to let the train in. Okay, now in the ground frame of reference, because of Lorentz contraction, the moving train will look like it's shorter than the tunnel. So as the train enters into the tunnel at point A, the door at A will open and it will let the train in, and the train will be completely inside the tunnel when the tail enters the entrance at point B. So you can imagine that the door at the entrance will close. Okay, and then the nose of the train will reach the exit at point C, which is happening after B. So between B and C, both doors of the tunnels will be closed at the same time. And then at point C, the door on the exit will open and it will let the train out of the tunnel. Okay, but then if you're looking at the same situation from the train frame of reference, it's the tunnel that will be shorter than the train. So you might think that if the door at the entrance and the exit of the tunnel are closed at the same time, the train will necessarily crash, right? Because the tunnel is shorter. And the question is, in one frame, the train is shorter than the tunnel. So you can close the doors at both ends of the tunnel at the same time. But in the other frame, the tunnel is going to be much shorter than the train. So how can you possibly close both doors at the same time? And that is a very good question, but it's not a problem because in the moving frame of reference, this red line represents the length of the train, and this green line represents the length of the tunnel, and the red is longer than the green. So, the train is much longer. Okay, but if you follow how time progresses in the moving frame of reference, when the nose of the train reaches the exit of the tunnel at point C, the tail of the tunnel the tail of the train is still outside of the tunnel. Okay, and the door on the entrance of the tunnel is still open because the door doesn't close until you reach point B. Okay, and in the moving train's frame of reference, point B is happening after C. Okay, so when the nose of the train emerges from the tunnel at C and the tail finally enters at B or something, then the B is happening after C, so the door on the exit is open before the door in the entrance closes. Okay, so the two doors are never closed at the same time in the train frame of reference. And that is the reason why it doesn't crash. Okay, in one frame, the train is shorter than the tunnel, and therefore, and B happens before C. So in between B and C, both doors are closed, and the tunnel and the train is completely fitting inside the tunnel. But in the train frame of reference, the train is much longer than the tunnel, but C happens before B, so there isn't a single time at which both doors are closed. And that is the resolution to the problem. Okay, and since I am running out of time, I think I'll skip some slides, but basically you can figure out why Doppler effects happens, because when you think about the Doppler effect in sound and the Doppler effect in light, the reason why the Doppler effect happens in sound is because the speed of sound depends on the observer. Because if you're moving relative to the air, the speed of sound will be different, and that leads to wavelengths of the sound changing depending on the motion of the source or the motion of the observer. Okay, but in the case of light, the speed of light is the same for all observers. So you might wonder, how can you have red shift and blue shift in light if the speed of light doesn't change? And the answer is, even though the speed of light may not change, because the concept of at the same time changes depending on the observer, what you consider the wavelength of the light pulse is going to be different depending on who's doing the observation, and you can always show that the wavelength is going to be longer if the source is moving away from you. And you can again do that using a space-time diagram. And if the source of the light is moving towards you, you can also show that the wavelength will be shorter every time it sort of changes direction and comes back towards you. And you can also do addition of velocities using space-time diagrams without using any equations. And in this diagram, I show how to add half the speed of light to half the speed of light. Imagine that three objects start at the exact same point in space, and you wait some time, and then you look at the spatial separation of the objects. And if the speed, then the spatial separation of the objects will tell you the relative speeds of the object, right? For instance, if you have a car, a baseball, and a tree, and two light pulses all emerging from this space-time origin, then if you sort of wait a while and you sort of freeze the frame, so to speak, to sort of figure out where the two light pulses and the three objects are at the same time, you will find that the light pulse that went to the right and the light pulse that went to the left are equal distance from your car, if you're using the car frame to look at it. And the ball that was moving to the right at half the speed of light will be halfway between your car and the light pulse on the right. And the tree that was moving at half the speed of light to the left will be at half distance compared to the distance that the light pulse has covered, right? So all you need to do to sort of look at how velocity is at is actually to sort of have all the objects start at the same point, and you sort of freeze the frame after some time and look at the separation, relative separations of the objects, okay? But, you know, the tree and the ball are both equal distance from the car and moving at half the speed of light in the car frame. But if you look at the same situation from the tree frame, in the tree frame, the points that are at the same time will be different. And when the tree is at this point, the points that are at the same time as this point and the points that are lying along this line. So in the tree frame, when the tree is here, the car is here, the ball is here, and the light pulse is here. And then you look at the separation of the objects, and you can easily see that the distance covered by the baseball is 4/5 of the distance covered by the light pulse. So when you add half the speed of light to half the speed of light, it's going to be 4/5 of the speed of light. And so on and so forth. So, so please excuse me for sort of skipping a few slides. So what we can conclude from playing with these diagrams is that clocks in frame B will be running slower compared to clocks in frame A if you observe it from frame A, and vice versa. Clocks in frame A will be observed to be running slower compared to clocks in frame B if observed from frame B. And length in frame B observed to be shorter compared to length in frame A if observed from frame A, and vice versa. And we come back to the question we posed in the beginning. How can both points of view be correct at the same time? And the answer is they are both correct, because at the same time in frame A is not the same thing as at the same time in frame B. At the same time is a concept that depends on the observer, okay? So asking the question, how can both points of view be correct at the same time? The answer naturally is, of course, you can't have them both correct at the same time. They're both correct because they're not at the same time, roughly speaking. So that is that. And I think this method is a method that avoids using equations, and it is accessible even to people for whom math is a little bit challenging. And for further details of the method, please look at my book. I hope it's in your library. And thank you very much for tolerating with me. I'm afraid I went a little bit over time.
Thank you so much, Professor Takeuchi, for this. I had never thought about like we can teach special relativity completely by using the space-time diagram. So this is an excellent talk. And again, I'm taking the same sentence from you. For those for which for who has like kind of difficulty in like doing mathematical expressions and like that, like, so this visualization is excellent, right? So thank you. So since we are over the hour, like, so if there are one or two questions, like, will you be able to take one or two questions if there are any, Professor Takeuchi?
Oh, I can sort of stay for another 30 minutes if necessary.
Okay. So please, if you have any questions, unmute and ask the speaker. Thank you. Maybe a couple of questions.
Quick one.
Yeah, please.
Yes.
So thank you very much for a very interesting talk. It was mind-boggling to see the pictures, and I'm trying to like track the lights to basically explain the correspondence there. So people learn differently. Some has a strength in math, some have strength in their visualization art, and then I think we are trying to tap onto that visualization skill here, right? um,
Yes.
so if in your classroom, if there are students who came in with a strong math background, and they don't have the geometric, that visualization skill that you are tapping on, how would they compensate for that? Because we are trying to like address that issue where people have difficulty in math, right?
Yes. Yes.
And in this case, sometimes people have like a poor drawing skill, or corresponding to that concept.
Well, if you require the student to draw diagrams, yes, some students have issues with that, but I think they can all be taught how to read space-time diagrams. So when I teach special relativity in my class, the exam problems, I always provide the space-time diagram and ask them questions like, for instance, if I have a space-time diagram like this, I would have various points on the diagram labeled A, B, C, D, F, G, H, I, J, K, or whatever. And I would ask questions like, if the tree is at this point, uh, where's the car at the same time in the tree frame, for instance? And then the student can sort of choose the space-time point that corresponds to the right answer. And that way they don't have to have very good drawing skills. And I find that many students like that approach. And I think it works. And also, in the long run, if you eventually want to teach students general relativity or something like that, I think this drawing approach is much better than the usual approach to general relativity because, the Lorentz transformation equations are already difficult. And when you generalize it to general coordinate covariance or something in general relativity, then it becomes extremely difficult for the students to really understand what the hell is going on. But in the case of, but if you draw diagrams or something, the difference between special relativity and general relativity is that in special relativity, you're doing these coordinate transformations on a flat sheet of paper. But in the case of general relativity, space-time is warped. So it basically corresponds to trying to do this on a piece of paper which is kind of warped, like a surface of some curved, like a curved surface. And I think that idea is easier to introduce because we talk about curvature and Ricci tensors and that kind of thing in general relativity. And if you actually have a diagram that is actually warped, I think it's very much easier for the student to grasp what you're talking about.
Yeah, great.
Awesome.
Does that answer your question? I
Yes,
hope.
yes, that was my next leading question. Actually, you answered it already. Because whenever it's on the flat surface here, we don't have any gravity, for example. And then my next question was going to be like, have you done something like that in class where you try to explain the gravitational rate shift using the curved analogy of that foam or
Well,
the sheet?
yeah, yeah, I haven't done gravitational redshift, but I do try to explain what would happen when you have an accelerated frame. Okay, because because special relativity only deals with inertial frames, but the moment you introduce acceleration, it becomes very interesting. Because let's see, let me share with you. Let's see now. I wonder if I have. Oops. Well, let's see. Let me try to sort of explain it using the. Let's see. So the Lorentz transformation takes you from like this uh, square lattice to this diamond lattice, and depending on your speed, this coordinate system will be different, right? So imagine that you're in a frame which changes its velocity, like the twin paradox diagram. Oh, I think the twin paradox diagram is much better. So in this twin paradox diagram, the spaceship is in an accelerated frame, right? Because it changes velocity at point C, right? And so up to point C, the spaceship frame of reference will be the coordinate, will be the inertial frame moving to the right, okay? But after C, it'll be the coordinate system moving to the left, okay? And because C is simultaneous with A and C is in the outgoing frame and C is simultaneous with B in the returning frame, you can use the returning frame of reference, the left moving frame of reference, in the upper half of the space-time diagram above the line that connects B and C. Okay, but you can't use it for the area below that line, right? And in the same fashion, if you look at the right moving frame of reference, you can use that up to point C, because that's the point in which you change direction. So you can use that coordinate system below the line that goes through points A and C, okay? But in the triangle area that's made by BCA, in this area to the left, neither coordinate system would work. So you need to basically introduce a more generalized coordinate system, which is not obtainable by a Lorentz transformation. So I think when you introduce acceleration, you can motivate the introduction of more generalized coordinates. Okay, and also when you go to more general, if you go to an accelerated frame, you can also explain why you can have black holes. Okay, and that doesn't require that much of stretch. Let's see. Okay. I'm sharing another file here. Can you see this? I'm showing a
Yes.
space-time diagram, which
Yes.
is in gray.
Mhm.
Okay. So imagine that you are following this hyperbola. Okay. So you are accelerating at a constant rate to the right. So you are heading towards the origin in the beginning, but then you turn around at some point and then start accelerating to the right. And if you are accelerating at a constant rate, then you will be following a parabola like this. And this line at a 45-degree angle is going to be the asymptote of your hyperbola. Now, if you're following this hyperbola, you are always moving at a speed smaller than the speed of light, because you're going to keep on approaching this 45-degree line, but you're never going to become parallel to it. So you will keep on accelerating, accelerating, and accelerating. You will keep on approaching the speed of light, but you'll never reach it. Okay, what that means is that the light pulse that is emitted anywhere in this gray region will never reach you. Okay, so the light pulse, for instance, that's emitted from the origin is going to chase after you at the speed of light. And even though it's moving at the speed of light and you're always moving at the speed which is smaller than the speed of light, that light pulse will never ever catch up to you. Okay, so this region on the space-time diagram is basically beyond an event horizon, because if you're an observer that's sort of following this path, you can never have any access to it. So a black hole is basically something like this. You can have light coming out from a black hole, but it's never going to reach you. And they never come out of the event horizon. So once you start thinking about accelerating frames, event horizons come out naturally. And if you explain that using accelerating frames, I think it's much easier to accept black holes when you introduce gravity, which amounts to allowing this flat space to work. Right? I
Thank
mean,
you.
globally, if globally, the equivalence principle says that you can get rid of gravity by going to an accelerating frame. And if the frame is if your sheet of paper, if your space-time is flat, then what happens is that in an accelerating frame, you can sort of you have something like gravity, but you can always make it go away completely throughout space-time because your sheet of paper is flat, your space-time is flat. But in real gravitational situations, you can only make gravity disappear locally. Okay, because real gravity has something to do with the curvature of space-time. And if the space-time is really, really curved, you cannot have a global coordinate system that would work.
Okay, thank you so much. Very interesting question and very answer very in details. Thank you, Professor Takeuchi. Probably at this point, like we are half an hour beyond our
Yes,
time. So
sorry.
no, no, this is great. This is great. This is great. Like so, at this point, probably I'll stop the recording. Let me stop.